A moment to set up my stuff.
Oh, it's okay.
I'm not putting the entire row here. Right. Sure. Okay. So we should introduce the speaker. So, okay, ladies and gentlemen. So it makes me great pleasure to introduce Goran Žužić. He works on very interesting problems, and as you may know, has a very strong background in competitive programming. And following this, he went on to pursue his passion for computer science by doing a PhD at CMU with Bernard Hoypler. And currently, he's a postdoc at ETH Zurich. During his PhD, he worked on some very exciting problems in distributed computing, where he made some very interesting connections between problems that people care about in distributed computing and various areas of computer science, such as graph theory, metric embeddings, and information theory. And for this work, he was recognized with the ACM EATCS Principles of Distributed Computing Doctoral Dissertation Award. And he's going to tell us a couple of words about his work today. So let's hear him out.
Thanks so much, Adrian, for the really nice introduction. So hi, everyone. I'm Goran, and so I do theoretical computer science research that mostly focuses on distributed computing. So today I'll be talking about a concept called universal optimality in distributed computing and its connections to diverse areas of theoretical computer science. So the talk is going to cover quite a long sequence of papers that I have actually done during my PhD, as well as some follow-up work that happened later as I'm currently a postdoc at ETH Zurich. There has been a long list of co-authors that actually I had been done with this work, so I will not mention that explicitly, but yeah, of course, not only me, but many people that were collaborating with me on this. So let's start. I will start by giving you a little bit of context about like distributed computing and why we studying it. So first off, so that we are on the same page, the main question in distributed computing is like how to design systems of independent nodes, like computers that send messages to each other, right? Just so that we are on the same page. So such systems are very diverse. So a few important examples that you can keep in mind is like, for instance, distributed databases that are processing data that are too large to fit on one computer, or chips on a supercomputer that are perhaps trying to synchronize with each other, or perhaps protocols running on the internet. So hopefully, like the ubiquity and importance of these examples is going to show you that this field is like full of very important results. However, many of these results are, let's say, unintuitive, like in the sense that if a person is trying to implement these distributed systems without a good understanding of the underlying principles that are actually happening below, they will quickly run into fundamental issues that aren't really able to be dealt with without like complete redesign of the system. So you cannot debug them away. You would need to redesign the entire system to get away with it, to like correct them. So let me actually illustrate this with a few results, with a few like examples. So those of you that, probably had operating system in, your undergrad studies, which is probably most of you, might remember like trying to get a mutex, a mutual exclusion, to work in a parallel multi-threaded system. You might also remember there is a, relatively straightforward, a relatively easy solution that was quite innovative at the time, known as the Dijkstra's algorithm, and that solution is taught in an undergraduate class. On the other hand, once you move to the area of distributed systems, trying to achieve mutual exclusion now is going to the territory of the notoriously complicated consistency protocols, such as Paxos, and those are much harder. So second, there are many types of very natural distributed systems that you might ask for that just turn out to be impossible to achieve. And one needs to be very careful about choosing the trade-offs which you want to keep and which you want to eliminate in order to make the system actually, doable and implementable. So let's say another example, like a blockchain, which, as you all know, studies how to perform tasks in a low trust environment between rational agents. And here, the trade-offs that are possible in such a system have wide-reaching consequences to the world today. And finally, as a fourth example, and perhaps the example that is the closest, that's the one that I'm going to tell you today. We have like massive graph analytics and data processing engines like Prego or MapReduce that are essential to the tech companies of today. All right. So furthermore, as you'd imagine, the world is becoming more and more decentralized. And because we have big data, requires more computers to fit in, and the slowdown of Moore's law that says that we're not going to have exponential speedups for much longer, makes decentralization and the study of distributed computing as a field of increasing importance. And the point that I'm trying to make is, so in the future, we won't have much choice but to actually try to build fast and reliable distributed systems. But as these examples above show you, building them requires a solid understanding of the fundamental principles of distributed algorithmics. And in order to achieve the trade-offs that are inherent in such a system, in order to know what you can actually build and what you cannot. Okay, so let me tell you a little bit of a context about my research and about how does my research in a big picture look like. So the research direction that explains most of the work that I have done is the following one. Suppose you have nodes in a large network that want to collaboratively solve some problem. Your task is to design an ultra-fast and simple algorithm whenever possible for this task. What are the fundamental barriers preventing these ultra-fast algorithms from existing? All right, and let me elaborate a little bit. So here by a network, I just mean like a bunch of computers that are interconnected by some abstract edges. And by edge, you can think of a cable interconnecting computer or just a satellite link or anything like that. So you should think about, like, when I say a network, just think about an undirected graph in computer science. These two words interchange. You can interchange as much as you like. So as a nice problem to keep in your mind, you can think of finding the shortest path between two computers in like some huge network. So to be a little bit more concrete, we will define the shortest path problem in the following way. You have a network, and each edge of this network has a rental cost, like cost to rent this edge. And now you want to find the minimum cost to connect two given computers in this network. So as another problem that's very important, we can define the minimum spanning tree problem, which is very similar. Each edge has a rental cost, and now you want to find the minimum cost to connect all computers in a connected subgraph, in a connected tree subgraph even, same thing. And finally, a third problem is the min cut problem, where each edge has a cost to destroy, and you want to find what is the minimum cost to disconnect the network into two parts. So today we will mostly focus on these three problems. But before I go into that, there is one very obvious question, like, why do we even talk about them? Why do we even study them? Well, let me give you a few reasons before I go actually how you do them and what are the results. So all these three problems have been studied to death in the classical setting for more than 100 years. They have been used as a testing ground for new ideas. Whenever there was like a new advancement in these problems, it has been typically directly applied to a plethora of new problems, and that had led to like advancement in many other problems of interest. As a second example, even in the distributed setting, the problem of the minimum spanning tree has been one of the first problems ever studied, and it has been studied for more than like 40 years. And despite all of this research that has been done during that time, we still don't really have a good, definitive, concrete answer to what is the fastest possible solution to this like extremely important problem of minimum spanning tree in the distributed setting. And as a third example regarding this problem of minimum spanning tree, there even exists like a standardized IEEE protocol called the spanning tree protocol. We should tell you that someone, at least in practice, somewhat cares about these things. All right. So that's it for the introduction. So let me tell you a little bit how the talk is going to go on from this point on. So first, this is the theoretical computer science talk. So I will define you the mathematical model of message passing that I will work in, as we will assume as the communication model for our tasks, in order to make this fully formal. Then I will define the main concept of the talk, which is called universal optimality. So this is a very strong notion of optimality in distributed computing. Well, I wasn't the one that actually defined it. It has been defined more than 20 years ago in a landmark paper by Goran Žužić. But essentially, no progress has been made on the question, is it possible to actually achieve this universal optimality? But let's say a year ago, my co-authors and I actually showed that this notion is actually possible. And I will talk about it through the rest of my talk. Finally, I will actually tell you that what are the various connections of this universal optimality, diverse topics of theoretical computer science that have popped up as we try to, make it happen. So I will show you a couple of different connections, 6 to be exact. I'll show you a connection to natural graph algorithms, new distributed notions of complexity, a connection to network building apps, to oblivious packet routing, to graph embeddings, and to provably fast algorithms. Well, if we don't have time, I might skip a few, but hopefully I'll get through all of them, and this should be fairly quick. So let's start. Okay, let me define you the model first. So the mathematical model that we're going to assume is like a standard message passing model, like the first one that would come to mind if you try to formalize this notion of message passing. And in the field of distributed computing, it is known as the congest model, which is written right above there. So in this model, the network is modeled exactly as an undirected, unweighted graph, G. This graph G, we say, will have n nodes. There's going to be a parameter that we're going to keep track of, and has a hop diameter of d. So, for example, you can see the network on the right. It has 7 nodes and a hop diameter of 3. Right, just as an example. So communication occurs in synchronous rounds. That means you have like round 1, round 2, round 3, and so on. And you can do local computations on the computers in between. During each round, neighboring nodes exchange small messages with each other. And here, by small, I mean polylogarithmically many bits. So from this point on, I will use this like O tilde notation to hide polylogarithmic factors. And the reason for this is because this theory that I'm going to tell you becomes very nice if I ignore polylogarithmic factors. And before this line of work, the theory was very much unsettled, even for much larger polynomial factors. All right, so initially, nodes only know the neighboring inputs, so like the edge codes. In particular, nobody knows the entire network. You need to learn the network as one of the issues that you need to deal with. So the objective that you want to minimize is the number of rounds until all the nodes know the result. So for instance, in the minimum spanning tree problem, you want to minimize the number of rounds until all the nodes know the minimum spanning tree weight. And good, so as a note, so D does not depend on the edge costs, but is a topological property of the graph. Like if you imagine on the network above, the hop diameter D is always 3, even if the edge costs are completely unrelated, like hundreds or whatever. The hop diameter is 3. It talks about the communication cost, not about the input cost.
So the hop diameter, just the diameter? Or?
Yeah, hop diameter, I mean, because there are kind of two things. There is like edge, which is 1 always, the hop of 1. And there is an edge cost, like a rental cost that you need to pay to buy this edge, which can be whatever, like $200, 200 euros. And these things are completely unrelated. So I just want to say hop diameter is the natural one for communication. So just to be, to verify that we're on the same page, I'm just going to go and give a simple example of broadcast. So imagine your task is to broadcast a single message from one node to all the nodes. Let's solve it in the most natural algorithm ever, which is just saying every node that currently knows the message just spreads it to all the neighbors. So what's the number of rounds until everyone will know the message? And repeat it, and repeat spreading until we stop. What's the number of rounds until everyone knows the message? Yeah, it's like D. You need D rounds, and after D many rounds, everyone will know the message. I just want to show you that D is an important parameter for this kind of questions. Yeah.
Yeah, a few questions about the model. So, do the nodes have identifiers?
They do.
Okay. And I guess the broadcast, we suppose that the message is of polylog size, because otherwise one round is not enough to share it with your neighbors.
Sorry, what's
the message size is, I guess, yeah.
Logarithmic. You're asking why is that the case?
No. Just the third question. Basically, I'm used to hear that the congest usually is a logarithmic size. So you are generalizing the fact that now it's polylogarithmic?
Oh, good. So, yeah, so typical congest model is logarithmic, but I'm generally ignoring all the polylog factors throughout the entire talk, so just to make it consistent. Okay. You're absolutely right. Nothing changes if it's like log or polylog, because I'm generally ignoring polylog factors throughout this talk. So yeah, this model is a model that tries to model the congestion issues that arise when you're trying to design protocols and like distributed algorithms.
While we're on the model, can you address distinct messages to your different neighbors, or are you okay?
You can. Yeah. So a node communicates different messages to different neighbors. Yes, it is not a, as they call it, a broadcast model. The most general case. All right. So, good. So when discussing the problems of today, we will typically be very happy with the runtime of D. And so you can imagine D as being small. There is a few, reasons why, this is okay. Like a more, applied justification for this is when you're talking about any, real world network of interest, they typically have like either a tree-like or an expander-like structure, meaning that the diameter is going to be polylogarithmic. Because, it's like a binary tree, it's a logarithmic, or an expander, diameter is logarithmic, it's fine. And some combination of this, usually you keep this property. On a more theoretical justification, for any of these problems that I talked about, MST, Minka, whatever, you really need this diameter. You cannot ever hope to get anything faster than the diameter time. For example, imagine solving the minimum spanning tree on a cycle. You need to find the heaviest edge and not include it. Well, in order to find the heaviest edge, for every node to know which is the heaviest edge, you definitely need to tell what is the cost of this heaviest edge to everyone. So if the diameter is like D and you have an algorithm that's faster than D time, you like some of the nodes will definitely not be able to know the heaviest edge. So you need D time. You cannot do anything without D time, and that's kind of a nice small parameter to aim at. So for the rest of the talk, I will talk about the problem of solving the problems of minimum spanning tree, shortest path, and min cut in this distributed message passing congest model. That's what you should keep in mind. However, before I'm gonna go towards the results, I'm gonna set the stage a little bit for you about the results that were known before I started my PhD. So what was known is that after polylog, square root n plus d algorithms were known. What does that mean? Any network, you can solve it in square root n plus d many rounds. The d is fine, as we said before, that's like a small factor, as you should think, but the square root n is huge. And you can imagine, in a network of interest, the number of nodes is huge, but the diameter is small. You do not want this square root n. But okay, that was what was known. However, there exists a pathological family of graphs, the ones that are depicted on the right, where you actually need this many rounds, even though the diameter of this graph is logarithmic because of the tree on the bottom. The diameter is logarithmic, but you still need square root n rounds. And this kind of shows you that you cannot really do much better than the first result. So are we done? Is everything solved, right? But a little bit more was known. we knew that for planar graphs, one can do much better. One can do all tilde of diameter many rounds. And this would kind of show you, that the question isn't really done by just considering the first two results. But this is more or less all that was known. So this kind of poses an obvious follow-up question. So do network of interest that you want to solve your problems on really look like the pathological graph, like the one here, in which you cannot do anything better than square root n plus d, or the square root n being the barrier here?
Sorry, just a question.
Yeah.
Is it the same algorithm that you use for planar graphs and general graphs, or do you have to design a specific one for planar graphs to reach this the complexity?
These were different algorithms, yeah.
Yeah, okay.
Like actually, this one was actually an inherent square root n. Like
Similar question.
you did some sampling for square root n rounds, and yeah, you run it. This algorithm, the first algorithm, you run it on any graph, even a very simple one, it will take square root n rounds inherently. All right, but the question is what about real world graphs? Can you actually design order 3 ultra fast algorithms for any real world graph that you care about? And that was really not known. So kind of the question that I started during the PhD is can we be more helpful in our answer? Can we actually design fast algorithms for networks that we care about that actually depend on the network structure and adapt to them, to the structure at hand? So the question was actually posed in a landmark, almost 30-year-old paper now by Garai and Peleg, that asked which graph parameter characterizes the complexity of distributed minimum spanning tree and other problems. And is there an algorithm that is as fast as possible on every network graph that you happen to run it on? So, but despite the age and the prominence of the question, there was no progress that was done until very, very recently. But as I hinted before, the answer is yes. That's kind of the problem that we solved in many, many ways, and such algorithms also do exist. So so such algorithms do exist. And I will also tell you this graph. What is the graph parameter that characterizes these problems? So let's talk about universal optimality, which resolves the question that were posed before. So in a nutshell, universally optimal algorithms. Well, a universally optimal algorithm is a single distributed algorithm that, when run on any network G, is competitive with the fastest algorithm of G, competitive up to polylog terms. All right. So a little bit more formally, there exists some combinatorial graph parameter x of G, such that lower bound x of G is a lower bound on the number of rounds. So any correct algorithm running on network G requires at least x of G rounds. All right. So x of G is a lower bound. Furthermore, it's an upper bound in the following way. There is a single algorithm when run on G terminates in x of G times polylog n many rounds, but there is an asterisk, uses polynomial preprocessing rounds. So you would ideally not want this, but that's the first result. You need the polynomial preprocessing rounds. And what does this mean? Before you get to see the input, before you get to see the rental cost, the edge cost, you get to preprocess the graph however you want in polynomial time. And finally, there is a way to remove the asterisk. Ghaffari, Hyper, and Reke showed in an unpublished work that you actually can remove the asterisk and get always universally optimal algorithms for the most interesting case of this parameter being small, subpolynomial, n to the little of 1. When I say subpolynomial, I'm going to mean n to the little of 1. And such algorithms terminate in n to the little of 1 rounds, which would mean they are universally optimal up to n to the little of 1, so subpolynomial factors. And furthermore, in a further also unpublished work, the same authors actually show that it's possible to do this in all the graphs. So the thing to remember is, up to many different papers that are needed to actually make this happen, universally optimal algorithms are possible in every graph up to subpolynomial factors. So universal optimality is achievable. So this is very strong. This is a very strong notion of optimality that you should, intuitively think like algorithms at the University of Optimal perfectly adapt to the underlying features of the network. Yeah.
X of G quantify how we are near of the pathological case of.
Oh, I'm sorry. Could you speak up, please?
So just basically it's about this combinatorial graph parameter.
Yeah.
Does it quantify how we are near the pathological case of before, or it's more complex?
Yeah, it will quantify like if this X of G is square root 10, then you're basically looking at a pathological worst case graph. Yeah, if that's answering your question. So for a simple graph is going to be D. For a worst case example, it's going to be square root 10. Make sense?
But it's easy to compute if you have the graph.
It is, yes.
You don't have just bound on.
Yeah, not only is it easy to compute, you can make an algorithm that runs it that time.
Okay.
But I'll talk a little bit more about
Okay.
it. Yes.
So just to be sure about the model, we don't know the structure of the graph.
No. Okay. Well, I mean, if you have polynomial preprocessing, you can learn it before seeing the input. But if you use the third result, then you don't even know this.
Because I have to synthesize the polynomial in number of rounds.
Yeah, polynomial
It's a lot, yes.
number of nodes. I mean,
Yeah, so it's a lot.
yeah, that means you can learn the structure. I mean, that means you know the topology in advance. That kind of.
Okay, so this you know.
So here, yes, you know the structure in before, but not the input. Here, you do not know the structure nor the input. And it's always possible. So, sorry. Well, the answer is you do not need to know the structure. It is always possible. That is a simple answer. But there was a long sequence of papers that needed to be done that need to be done, and some of them are still unpublished that actually achieve this. So that's why I'm just saying it's in a more complicated way. Sorry, does this make sense what I said?
I think I understand. So basically, when you have the guarantee that the xg is small, it's sublinear,
Yeah.
then you can manage.
Yeah, and you can actually manage. Well, there is further unpublished work that says you can manage always, even if it's not small.
Okay, so let's see later.
Yeah, well, I won't really talk about it much. I'm just saying it's always possible. That's what you need to remember. Yeah, 2 questions.
I'm just wondering if the polynomial preprocessing phase assumption can be rephrased as, or is equivalent to saying that in addition to the input, you get the graph as input. Does that work?
Yes, that's exactly. Yeah, that's exactly equivalent. Yeah, perfect. Another question, but you do not need that with this new unpublished results.
Yes.
You don't need the graph, you don't need the input, you just run this single one algorithm and it happens to run optimally fast. Another question.
Sorry. If you tell X of G is helpful.
Yeah.
So instead of the polynomial processing, you just give X of G.
No, that's not.
It's not enough.
No, you need some heavy duty combinatorial structures called constrained oblivious routings. I mean, otherwise you would just binary search it, right? Okay. So, a question that I, get when I was trying to, give my friends the version of this talk. Okay, fine. You're talking about X of G, but what is X of G? How do you compute it? Like, what exactly is it? So let me preempt this question and tell you exactly what it is. So this is going to be a little bit of more of a technical side. So maybe you want to focus a bit more on this one. So what is X of G? Well, X is a function that takes as input an unweighted, undirected graph G, and it spits out a number like 17, right? Spits out an integer. But how is it defined? And I'll tell you, it's defined in a certain 2-player max-min game. So the first player chooses node disjoint paths P in our graph G, and I'll show you a choice of them now. So the first player chooses some paths that are node disjoint, one in red, one in blue, one in orange, one in green.
Do they have to cover the graph?
No. But if they do, it doesn't. But yeah, they don't. Furthermore, then the second player wants to minimize the number of rounds in order to exchange one bit of information between all the endpoints of the corresponding paths. So basically, if you look at the picture, so for every path you put like like a demand pair of the endpoints, and these pairs of nodes want to exchange one bit at the same time. All of them wants to exchange them at the same time in the same graph. What is the minimum number of runs you can make this happen? This problem is known as the multiple unicast problem. So let's say more formally, given multiple node pairs, exchange a single bit between each pair in a way that minimizes the number of runs. This is a well-defined max-min two-player game, and the result is exactly the definition of our X of G. I'll just note that in the literature we call this X of G the shortcut quality. I will not go why this is the case, but just if you see it in the literature, that's what the name of X of G is. But as far as you're concerned, you can think of it as a black box parameter that has something to do with the worst case multiple unicast. Yeah, question?
Yeah. I guess I'm missing something in the definition because I don't see the incentive to take more than one path in the max part. If you take the path between two nodes that are the farthest possible.
True, then you get diameter, right? But there are graphs where I can take many long paths, but if you want to communicate between them, not all of them can take the shortest path because then you're going to have congestion issues.
I see.
On the bottleneck edges. So that there is an interplay between the dilation and the congestion that is going to happen. So there are examples like the pathological worst case example that I showed, where you choose these longest paths. Now, the shortest way to connect them is through the tree, but the tree has a low throughput, and you would actually need to pay way more time in order to communicate between them. Oh, good. Thanks. That's actually a very illustrative example. Sorry, I hope it made sense. But okay. All right. So finally, I know this kind of defined the notion of universal optimality. And now I will go in the second part of this talk when I will talk about like the various connections of universal optimality to other diverse areas of computer science. I'm going to present like this 6 connections. They're all going to be like one slide, and hopefully they'll be mostly independent. So, if you happen to be lost in one of them, feel free to, wake up when the next one starts, as, they should be as independent as possible. So let's start. The first connection that I want to, showcase to you is one with natural graph algorithms. So remember how X of G has something to do with the time in which you can solve any multiple unicast problem. Assume you can, so let's say differently, assume you can solve any multiple unicast on all disjoint paths in X of G rounds. Imagine you know how to do it. X of G is just saying how long, but imagine you even know how to do it. Now, using this as a primitive, we can start building up higher level primitives by calling this like polylog many times. We can build up, I don't know, a certain primitive that is called partition aggregation, which I'm not going to define. And then, even building this up a little bit more, you can build up a very, very nice high-level primitive called minor aggregation, just by knowing how to solve these multiple unicasts. But let me tell you what this minor aggregation primitive that you can build up is. So a minor aggregation, you can imagine it as an oracle, which allows you 2 operations. It allows you to contract arbitrary set of edges, and it allows you to communicate certain, like each node will get an aggregate of its neighboring nodes after the contraction. So imagine you contract some edges. Now every node publishes a value, and then all the nodes get the sum or the max or some other simple aggregate of its neighbors. This is called the minor aggregation because you're operating on minors because you're contracting, and then you're getting aggregates of your neighbors in this minor. Now the idea is that if you have access to this primitive, you can actually model many graph algorithms in a very simple and natural way, using this as your, only interface to the model. So let me give you a very simple example of the minimum spanning tree. So you might know Borufka's algorithm. So just so I know, how many of you know Borufka's algorithm? Yeah, so it's like the simplest possible algorithm for solving minimum spanning tree, and it kind of just says the following. Each node finds the cheapest edge around it and contracts it. Repeat for log n times. So, I mean, this is basically exactly what you need in the minor aggregation model. You contract the edges, you contract a subset of the edges that you did, and then you find the minimum edge around you, which is exactly an aggregation operation. So clearly, you can implement, minimum spanning tree by log many calls to the minor aggregation oracle. And the thing that I want to showcase here is, well, we know that we can solve multiple unicast and non-disjoint paths in XLG rounds. Then we can solve minor aggregation in XLG rounds. And now I should show you that we can solve minimum spanning tree of XLG rounds. And this makes it universally optimal because we know from other work that this is also a lower bound, as I said before on the previous slide, I guess. One before that. So this is actually telling you that because you can implement MSP as with minor aggregation, there is this universally optimal algorithm for it. Yeah.
The definition of aggregate of neighbors is not clear to me. What do you mean by sum of neighbors? What do you mean by sum of neighbors?
I imagine so it's just like every neighbor publishes some value. So every node publishes a value, and then the node gets the sum of its neighbors. And you can publish a value, with respect to, you can kind of publish a value, or a little bit more generally, you publish a value on your adjacent edges, and then the node picks up the sum of the adjacent edges, or the max, or, basically any other associative operation that comes to mind. So yeah, you can contract edges and you can get minors. It's a way to talk about graph algorithms, and I claim it provides a very natural interface to them. So yeah, minimum spanning tree you can implement as minor aggregations. Another example is a problem of mincut, which in unpublished work that's going to be out very, very soon. We show that you can actually solve also mincut, exact mincut even, with minor aggregation, and that also gives it a universally optimal algorithms for mincuts. And a question that I spent a lot of time on was asking, can you actually reduce shortest paths, actually 1 plus epsilon shortest path to minor aggregations? Yeah, and the answer is yes. Yeah, sorry.
So mincut, the minor aggregation for mincut, is it similar to the Kargar's algorithm where you contract both edges?
Yeah. Oh no, it's not at all. Because that one is not very,
but still
you need to repeat it a bunch of times, right? You need to repeat like at least linear number, like n polylog n times. So no, it's more like the Kargar packing algorithm and then the two respecting tree cuts. It's like the one that came later. So not really, but yeah, we can talk about it later. But it can be done. You can reduce mincuts to minor aggregations. And also you can do shortest paths. You can reduce shortest paths, approximate shortest paths to minor aggregation, which was a problem, that I spent quite a lot of time, thinking. It didn't seem like that's possible, but yeah, that's like published in the recent SODA. And actually much more curiously, we actually showed that you can do near optimal parallel 1 plus epsilon shortest path. You can do in a deterministic way. You can deterministic approximate shortest path can be reduced to minor aggregations. And okay, why is this interesting? Well, even parallel algorithms were not known how to be done in near optimal time. Near optimal means up to polylog, optimal up to polylogs. And by showing you can actually do this by calling polylog many minor aggregations, this both implies a result in the parallel model because minor aggregations are trivial. minor aggregations and multiple unicasts are trivial in the parallel model. You just anything can communicate with anything. Therefore, this is trivial to do. I mean, these operations are trivial to implement in the parallel model. So now, by reducing deterministic shortest paths to minor aggregations, we solve the problem both in the parallel setting and the distributed setting. And I don't know, what was the last time that long-standing problem in the parallel setting was solved by looking at distributed frameworks, and how do you solve it in the distributed? I definitely don't know any time that happened. But the point that I'm trying to point out that if you think in terms of minor aggregations in your primitives, you're going to end up with natural graph algorithms that immediately work in both the parallel and the distributed setting, and that are nice in many ways.
Which model are you assuming for parallel? Can you say?
Theorem.
So it's a Piram model.
Yeah. I mean, the most natural one.
Yeah.
And if you just reduce the minor aggregate, you get involved. Because you can implement it in X of G time, short quality time, and you can implement it trivial in the parallel setting. So, the question you should pose yourself, can you solve your favorite graph algorithm with minor aggregations, yielding you results in many different models that are very natural and nice.
And another question, just on this slide as well, but in general, which one in this chain, which one are randomized? All of them are randomized, and which one are?
Deterministic. This says the packing algorithm is randomized, but then the rest is exact. So there is like a specification, like a subsampling part that we don't know how to. Like you want to reduce from a high connectivity to a log-n connectivity, and that thing, we don't even know how to de-randomize that in the centralized setting, even though there are some preliminary works of this. So basically, fully deterministic, basically deterministic up to one important part, but yeah, mostly deterministic. This one was randomized, and then we made it deterministic here. All right.
Where does the parameter xg figure out in this? So if we take the spanning tree example, the algorithm that you
it's a lower bound and it's an upper bound. It's a lower bound by some work. I mean, you need to believe me that some work. I mean, we showed that it's a lower bound, and this slide shows it's an upper bound. Make sense?
I wanted to see where the problem arises. Like, why is it like a lower bound? So, for example, in spanning tree, how does the parallel disjoint paths figure out?
Okay, I mean, not super easy, but the point is, I mean, how does the proof work, right? That's kind of the question. Well, the easiest way to see it, if you know how to solve spanning tree, you can design the gadget on a graph that allows you to solve, let's say, the disjointness problem between those endpoints. Like imagine like Alice knows one set of the endpoints, Bob knows another set of the endpoints, and you can solve the disjointness between Alice and Bob. And the disjointness essentially asks you to communicate one bit for all the endpoints. And in order to do this, you need to communicate basically, 1 bit per endpoint. How fast can you do this? Well, you clearly need to do this if you want to solve minimum spanning tree, and therefore that's a lower bound. That's kind of how the proof works, and I'm hiding many details that I'm happy talking about later. All right, might need to speed up a little. Well, I mean, there are 6, mostly independent connections. We can skip up here if I don't have time. But okay, let's go to the second connection, the new distributed complexity. Yeah.
Yeah, sorry. So maybe I'll ask you after the talk.
All right. So a new distributed complexity. So basically, on the last slide, I showed you that if you can solve multiple unicasts and multiple paths, you can solve all these problems, right? However, because of the lower bound, the reduction also works in the other way. So for instance, if there is a fast exact minimum spanning tree algorithm, there is a fast multiple unicast. There is a fast way to do multiple unicast of non-disjoint paths. So therefore, all of these problems that I mentioned kind of form a new distributed complexity class of problems that are interreducible to each other. So if you solve any one of them, you can solve all of them. And moreover, this class features a very simple, complete problem of multiple unicast on all the joint paths. It's like the simplest problem you can think of. That actually, if you want to solve if you want to solve some, hard problem like the shortest path on your favorite graph class, all you need to focus on is solving this multiple unicast and multi-joint paths. And the way you do this, you can solve it for everything. So, these are reductions that we show in the Stock 21 paper. And the takeaway here is that, there is a new distributed complexity class of interreducible problems that all take this X of G shortcut cut time. And actually, for those of you, how many do distributed computing and know about the square root 10 lower bound that was known for all the problems? Does anyone? At least a few of you. Good. So you kind of this square root 10 lower bounds in distributed computing hold for every problem ever, every global problem ever, at least if you ignore the local coloring problems. Well, this kind of explains why. They're all introducible in a very strong sense, So, which is nice. It kind of explains, many of the results that we had before. All right. Let's go to the third connection, network coding gaps, that kind of goes into how do we actually solve this multiple unicast on some network that you give to me. So, as you've seen before, it's, if you can solve multiple unicast, you can do minor aggregations and you can do all the other, big deal problems that you can think that you might care of. However, the question is, how do you actually solve this multiple unicast problem? So let me tell you a little bit more about the structure, about how to solve the multiple unicast. So, as a reminder, what's the problem? Fix many pairs of nodes, S1T1, S2T2, the one you can see on the picture on the right. And you want to simultaneously exchange one bit between each pair, between S1T1, S2T2, S2T3, and so on. And you want to do this in a way that minimizes the number of rounds. How would you exchange the bits? What is a natural strategy to do this? Well, if you think a little bit about it, you would very quickly find a very natural strategy called store and forward solution, which is basically for every pair, you would choose a path between that pair that connects them. And the goal is to choose a good set of paths. And what would you do? So you find a path between SC and TI, and then you forward your bit along that path. All right, just one moment. Now there are a few issues that can arise. If you choose a path that's very long, this is going to take a long time. And another issue, if all of the paths use the same edge, that's also going to take a long time because of congestion. You want to choose a set of paths that kind of minimizes both the congestion and dilation. So, a little bit more formally, we say that the set of paths has dilation D if each path has more D hops, and has congestion C if each edge is contained with more C paths. And now, if you can do this, you can find a solution in order C plus D many rounds. Oh yeah, we have a question?
Yeah, I'm wondering what is the input of this problem? Each pair has the identifier of the other node, or do they have more information? Or do they know to
Well, currently I'm thinking I'm going to talk about an information theoretic bound. So imagine we know everything. We know the graph, we know the pairs, I'm just going to talk about some information theoretic bounds.
Okay.
We are not in any model. We're in the information theory model, whatever. If you want to, yeah, I guess that's the best way. Okay, so there is a natural store and forward solution to the multicast problem, right? Choose a set of paths, forward along the path. Fine. But now there is a general solution, like a coding solution that uses any strategy that you can think of. You can XOR bits, you can use error correcting codes, you can do anything you want, right? And a very natural question arises. What is the largest gap between this natural store and forward solution and this general coding solution? All right. So, and we know if the gap is small, we can kind of say, well, you just look for store and forward solutions. We don't care about anything else because they are fast enough. Like if never there is a big gap between them. So clearly store and forward solutions are, less general than the general ones. The general ones are faster, but the question is how much faster? Can they be significantly faster than them? Such questions are called network coding gaps, and they're very, very important in the information theory. And this question kind of corresponds to what is the network coding gap for completion time? Completion time means the number of runs until you finish. Unfortunately, such a completion time coding gap has not been studied previously in information theory. But if you want to understand the distributed complexity of solving these problems, you kind of need to understand this network coding gap. And therefore, me and my co-authors were working on it for some time. And we show a few things. So first, there actually do exist instances where the coding gap is super constant, even polylogarithmic. So, there exists an instance where the general solution is much faster than the store and forward solution, which, I found quite interesting. Because the prior results that usually say there isn't any gap. And I mean, it's kind of a strange thing because if you think of if you were to, I don't know, transfer some physical commodity like, I don't know, water between the endpoints, then it's easy to show that network coding gaps do not exist. There is no way to get a super constant bound. But, it turns out information is not a physical commodity. It's more, it's information. So you can do some coding, XORing tricks, coding, like error correcting code tricks to actually make it super constant fast, polylogarithmically faster. But on the other hand, which is much more interesting for our application, the gap cannot be too large. It can be most log squared. So if you're happy using the log squared factor, which we are, you can only look at store and forward solutions. That's all that you need to know. So good. In conclusion, we get the first network coding gap for completion time. On the other hand, the network coding gap that we studied before, like for throughput, and basically, well, the goal there is not to maximize the completion, not to minimize the completion time, but to maximize the rate of the bits that you can pass through the network. And there are very, very interesting connections between network coding gaps for throughput and circuit complexity. So if you were to prove some of the, some conjectures for the throughput coding gaps, this would imply new circuit lower bounds that are unknown. That would imply, new circuit lower bounds. And now a very interesting question that, I didn't spend too much time thinking, but it might be plausible that maybe these completion time coding gaps actually imply some kind of a circuit overbounds for depth, for circuits of depths of the circuits. The throughput one usually imply for sizes of the circuits. Possible. I'm not putting too many chips in it, but something to explore for the future. Does it imply, does this network coding gaps, new type of coding gaps imply new circuit overbounds? Maybe even if they are stronger, even in a conjectured conditional sense. Okay, so let me I'll probably have time maybe for one more oblivious packet, but I think which is probably my favorite connection. So let me set the stage for you. Our goal is to get universally optimal solutions for distributed acyclic minimum spanning trees, right? And the way we do is we reduce this to multiple unicast on node disjoint paths. And we want to be able to solve this near optimally. And we know it's sufficient to look at store and forward solutions to this. But now the question arises. How to do this? Well, we know the problem is, we need to find paths, given, set of pairs, we need to find paths that minimize this congestion plus dilation. That is sufficient task to optimize. However, we need to find paths between that minimize C plus D. However, the issue arises that you're doing this in a network, in a distributed set. So different pairs. Now we are in the distributed setting, basically what we got, the question that got asked before. Now every node knows only its partner. And now you need to do this distributively. And intuitively, at least, you can imagine if there are two nodes in one part of the network, they do not know what is happening in another part of the network. And you want this path to be chosen obliviously. You want an oblivious way to choose the paths. Well, this question has been studied in the literature under the name oblivious routing for congestion plus dilation. And it's kind of a well-established problem. It has far-reaching, theoretical consequences. For instance, if you are able to choose near optimally, like if there is a way to obliviously choose near optimal paths, then you can do packet scheduling in a network in a near optimal way, which is basically what we do here, right? Which is basically what we want. And as another example, like this kind of corresponds to the question of, is it possible to build an offline navigation app? So you have, people say, oh, I want to go from A to B, tell me which path to use. Is it possible to do this in an offline way, such that it is competitive with an online navigation app, even the one that knows the future? And furthermore, hopefully I convinced that this is an interesting problem. And it's not even clear, even mathematically, does a structure exist with these properties? Is there a way to obliviously choose and get near optimal results? Moreover, this question was listed in 2004 in a survey by Asmes et al. As one of the 8 major open problems in distributed computing. But very little progress has been made ever since. But luckily, we do manage to find a solution for this. And the answer is yes, there actually do exist these structures called, we call hop constrained oblivious routing, and the formal statement is the following one. For every graph G and every dilation V, there do exist a randomized way of obliviously picking those paths where the expected congestion is near optimal compared to the optimal way to connect them with paths of length at most D, and the paths have dilation of close to D. All right. So basically, there is a way, and it's very nice. So just tell me, so I'm kind of out of time. So usually this takes 60 minutes, right? And that's it. Well, in that case, let me skip I will skip the graph embeddings, how you make these oblivious routings and how you use them to do how you can solve hop constraint problems in a very nice way. That you can solve, these are very fast on many graph classes, and go and jump to the conclusion. But yeah, in a nutshell, I study fundamental questions in distributed computing, and I basically followed the lead, and it made me go to places I wasn't expecting. Like I wasn't expecting to do, I don't know, oblivious routing as I started to post questions about what's the best way to do minimum spanning tree in a distributed network. Well, happy when that led me, but the point is I'm here going to be at EDIF until today and tomorrow still. And whoever wants to get coffee, please let's do it. And here is a few examples of what you can bug me with. If you have any ideas how to connect any of this to your work, even theoretical or practical, feel free to bug me. Or I don't know, you just want to know more, or you just want to talk. Yep, feel free to approach me and talk to me. So thanks.
Okay, so I don't know if we want one very quick question, or otherwise we take them offline. Oh, maybe let's take them offline.
It's a quick
We had questions.
question, but not quick.
Yeah, good.
So you can, yes, you can turn it off.
All right. Thanks.